Now we are still on heat, and the last time we looked at heat capacity, and we agreed that heat capacity is actually that amount of energy that we shall require in order for us to raise the temperature of some mass of a material by 1 degree centigrade or by 1 Kelvin. Now, we looked at specific heat capacity. We looked at specific heat capacity, and we were able to discover that actually now when we bring in the idea of specific heat capacity, what we mean is that now we are going specific. We want now to narrow down to the amount of energy that we are going to require for us to change a unit mass by 1 degree centigrade, or rather to raise the temperature by 1 degree centigrade. I want to work on an example. Now, the question reads, a block of metal of mass 5 kgs is heated to 110 degrees centigrade and then dropped into 1.5 kgs of water. Now, if the final temperature is found to be 50, calculate the initial temperature of water, taking the specific heat capacity of water to be 4200 and that of the metal block to be 460. Now, as usual, we are going to start by looking at the information that we have been given. And number one is the mass of the block, which is found to be 5 kgs, or given as 5 kgs. The mass of water is given as 1.5 kgs. Now, initial temperature of the block of the block is found to be 110, that is initial, and the final for the block is found to be 50 degrees centigrade. Now the water also gets to 50 degrees centigrade, that is the final temperature, but the initial is what we are supposed to calculate. Now the specific heat capacity of water is 4200 joules per kilogram Kelvin. That of the block is 460 joules per kilograms Kelvin. Now, one thing that we discovered is that the heat lost will always be equal to the heat gained. In this case, recall that heat in itself is a form of energy, and when we talk about energy, we say that energy cannot be changed, or cannot be destroyed, or cannot be created. All what we can do to energy is transforming. We can only transform energy to other forms. Now, in this case, our block was heated to 110 degrees, then dropped into water, which was at a lower temperature. Therefore, our block gives out energy to our water, so that now the temperature of water will rise to 50, while that of the block is actually going to drop. Therefore, for the water to have gained some energy, it means some loss on the part of the block. But then, the amount of heat that the block loses is what our water is going to gain. Now, heat in itself is given by mass, the product of mass, specific heat capacity, and the change in temperature. This one is supposed to be equal to energy. Now, here we have heat lost, the heat lost, in this case by our block, will be given by the mass of the block. Mass of the block. This one we multiply by specific heat capacity of the same block and the change of temperature of the block. Now, let us substitute. Here, mass is given as 5 kgs. Specific heat capacity is 460 joules per kilograms Kelvin. And now, the change of temperature will be given by 110 degrees. This one we subtract the final temperature, which is 50 degrees. This gives us 138,000 joules. That is the amount of heat that the block loses, 138,000 joules. Now, the heat being 138,000 joules, this one is equal to the heat gained. The heat gained And the heat gained by water is given by the mass of water, the specific heat capacity of water, and the change in temperature of water multiplied together. Now, mass of water is given as 1.5 kgs. The specific heat capacity is given by 4,200 joules per kilograms Kelvin. And the change in temperature, we are going to take it as delta theta, now that we don't know the initial temperature of water. Now, this takes us to 6,300 delta theta joules. Remember that this is heat we are calculating. In itself is a form of energy. Therefore, the units are the joules. Let us equate the two so that we can work out the value of the change in temperatures. Heat lost is equal to the heat gained. Therefore, 138,000 joules is equal to 6,300 delta theta. Let us divide throughout by 6,300. So that now we have our change in temperature as 21.9 degrees centigrade. Remember that this change in temperature is achieved, this change is brought about when the water, the temperature of water rises from some initial figure to 50 degrees Celsius, which is the final temperature according to our question. Therefore, temperature initial is going to be the final temperature minus the change in temperatures. The final minus the change. Our final was given as 50 degrees Celsius, and this one we want to subtract our change, which is 21.9 degrees Celsius, and what we get is actually 28.1 degrees. That must have been the initial temperature of water. Therefore, the most important part to remember is that when you're having two items which are exchanging heat energy, the amount of heat that is lost by one of them is definitely equal to the amount of heat that is going to be gained by the other. We will look at methods of determining specific heat capacity. And we have about 4. Number one is what we call the mechanical method. We have the electrical. We have the mixture method. And finally, we have the steady, or what we call the continuous flow method. We have those four. Now, depending on the set of operators that we have at our disposal, we can manage to apply any of those four, but they are supposed to give us the same result because all of them seek to determine the specific heat capacity. Now, I will want to look at them each one at a time. And I will start with what we call the mixture method. And the mixture method is where you have some item at a given temperature being mixed with others so that a steady temperature is now achieved. Now, to go about the determination of the specific heat capacity, you have to take care of each and every one of the items involved. So here, different items are mixed to achieve different items are mixed to achieve a steady temperature. But what you're supposed to understand is that the heat lost will always be equal to the heat gained. So in this case, we are going to look at more than two items and see how they relate in as far as absorption and loss of heat is concerned. Let us go about it by way of example. The question reads, a block of iron of mass 1.25 kgs at 120 degrees centigrade was transferred into an aluminium calorimeter of mass 0.3 kgs containing a liquid whose mass is 0.6 and at 25 degrees centigrade. Now, if everything reached a steady temperature of 50 degrees centigrade, we are supposed to calculate the specific heat capacity of the liquid in the calorimeter, and the specific heat capacity of the others is given. Now, here you understand that we are interacting with three different items. Number one, we have the iron block. Then we have the aluminium calorimeter. And finally, we have the liquid in the calorimeter. Now, we are supposed to come up with the specific heat capacity of the liquid given the information that we have. Now, let us write down what we have. Now, mass of the block is 1.25 kgs. Mass of the aluminium calorimeter is 0.3 kgs. Mass of the liquid is 0.6 kgs. Initial temperature of the block is 120 degrees centigrade. Now, initial temperature of the aluminium calorimeter is 25 degrees centigrade. That of the liquid is also 25 degrees centigrade. So the temperature final for everything is 50 degrees centigrade. Now, also we have the specific heat capacity of the block as 450 joules per kilograms Kelvin, and that of the aluminium is given by 900 joules per kilogram Kelvin. Now we are after the specific heat capacity of the liquid. Here, what is losing the temperature and subsequently energy is what we call the block. Therefore, we say heat lost by the block is equal to heat gained by calorimeter plus heat gained by liquid. Heat lost by the block is equivalent to what the calorimeter gains as well as our liquid. Now, but we know that mass, the product of mass, specific heat capacity, and the change in temperature is equal to all these are for the block. That one, mass of the calorimeter, a specific heat capacity of the calorimeter, and the change of temperature of the same, you add to that of the liquid, which is mass of the liquid, specific heat capacity of the liquid, and then the change in temperature of the liquid. Let us substitute the information that we have in our question. Mass of the block is 1.25. Now, specific heat capacity is 450, and the temperature change is from 120 to 50. 120 to 50, we subtract and get 70, is equal to mass of the calorimeter is given as 0.3 kgs. This one we multiply by its specific heat capacity, which is 900. Then the change in temperature, which is 50 minus 25, gives us 25. And then this we add to mass of the liquid, which is 0.6 kgs. Now, specific heat capacity is what we want, and then the temperature change is from 25 to 50, so we multiply by 25. Let us work out what we have. On the left-hand side, we have 39,375. These are joules. This one is equivalent to 6,750 joules. Then we add to we add to 15. Then remember that the specific heat capacity is still pending. We have not taken care of it. Let us now collect the like terms, and that will mean we subtract 6,750 from the figure we have on the left-hand side of our equation, which is going to yield $32,625 is equivalent to 15 multiplied by the specific heat capacity of our liquid. Now we can divide both sides by 15, so that now the specific heat capacity of the liquid becomes 2,175 joules per kilogram Kelvin. Therefore, you will have to take care of all the items that are interacting. For example, sometimes you could have even different solids that have been mixed together. You could have different gases that are mixed together. Of great importance is to remember that the heat lost is actually divided among the constituents of the mixture. It is always equal to what has been gained by the constituents of the mixture. Now, I want to take another example. A copper calorimeter of mass 0.75 kgs contains 0.9 kgs of water. All of them are at 20 degrees centigrade. So that one is what we are going to take as our initial temperature for the two. Then a bolt whose mass has been given as 0.8 kgs is transferred into the calorimeter, and the bolt is at an initial temperature of 400 degrees centigrade, and everything in the container achieves a steady temperature of 50 degrees centigrade. Now, having been given the specific heat capacity of the water as well as the material of the calorimeter, we are supposed to get the specific heat capacity of the bolt. Now, again, let us look at what we have. And what we have for the masses, mass of the bolt is given as 0.8 kgs. Mass of the calorimeter is 0.75 kgs. Mass of the water is given as 0.9 kgs. Now, specific heat capacities, that of the bolt is what we want to look for. That of the calorimeter is given as 400 joules per kilograms Kelvin. Then that of water is 4200 joules per kilograms Kelvin. Now again, we also have the temperature changes. That one of the bolt will be 400. We subtract the fine of 50, which will give us 350 degrees centigrade. Now, that of the calorimeter changes from 20 to 50, or rather rises from 20 to 50, depicting a gain of 30 degrees centigrade. Then we have that of water also changing from 20 to 50. Remember, we were told that initially the calorimeter as well as all what it contained had an initial temperature of 20. Now, after putting the bolt into it, a final temperature of 50 is what we achieve. Therefore, we are justified to say that the two were at 20 and their temperature raised to 50 degrees centigrade. Therefore, the change of temperature of water also is 30 degrees Celsius. 30 degrees Celsius. Now let us go through the working again. Let us go through the working again, and we remember that heat lost, in this case it's by our bolt, is supposed to be equivalent to heat gained by calorimeter plus heat gained by water. It's supposed heat lost by bolt is the same as the heat that is going to be gained by calorimeter added to that which is gained by our water. Now, therefore, the mass of the bolt multiplied by specific heat capacity of the bolt and the temperature change of the same should be equivalent to the product of mass of calorimeter, specific heat capacity of the same, change in temperature of the same added to the mass of water multiplied by its specific heat capacity and the subsequent rise in temperature. Now, with that, let us substitute what we have into our equation and see whether we can be able to go about calculating specific heat capacity of the bolt. Now, the mass is 0.8. We multiply this by what we are looking for, which is the specific heat capacity. This one we multiply by the change in temperature. Now, that part takes care of the bolt. Now we go to the right hand side, feed in the values in the equation. Now we take the mass of the calorimeter, which is 0.75. We multiply this by the specific heat capacity of the same, which we have been given as 400. Then we multiply by the change in temperature, which is 30. All that we add to the mass of water, which is 0.9. We multiply by the specific heat capacity. Again, we have it as 4200. Then the change in temperature, which is 30 degrees Celsius. The right hand side gives us 280 CB. C subscript B stands for our specific heat capacity of the bolt on the right hand side, which is the loss side. Now this one will be equivalent to 0.75. That is 9,000 joules. We add to 113,400 joules. The left hand side gives us 122,400 joules. That is after adding the 2, which is equivalent to 280 multiplied by the specific heat capacity of our bolt. So we can divide by that. The right hand side gives us this figure as our final, which is equivalent to 280. You multiply by the specific heat capacity of the bolt, and this one, after dividing throughout by 280, the other side by 280, gives us the value as 437 joules per kilograms Kelvin. So that's about all about the mixture method. What you are supposed to remember is that heat lost is the same as the heat gained by the constituents of the mixture. Heat lost is equivalent to the heat gained by the constituents of the mixture. We could now move on. Let us move on and look at yet another method. Now, let us look at electrical method, and on this, now we have moved a step further, where we want now to look at how we can be able to change electrical energy into heat. How we can change electrical energy into heat. So here involves changing electrical energy into heat. Electrical energy into heat. Now, here, the energy we require to raise the temperature of whatever we have will come from electricity. So, if we want, for example, to change the temperature of water, we connect a heater coil to our water so that we can realize the desired change in temperature. So here of great importance are three factors. We consider three factors. Number one is the voltage. Number two is the current. And the time. We have voltage, we have current, and we have time. Now, we remember that electrical energy in itself is a form of energy. Now we want to transform it to another form of energy. So we want to ask ourselves, now this current that we are supplying to our coil, what work has it done? Remember, we looked at work and we said it is equal to the amount of energy spent. So the amount of energy that you spend to perform a task is the work that you have done on that particular task in scientific language. So here, heat energy is equivalent to work done by the electric current. And the work done is given by the product of the three factors that we have listed. So therefore, is voltage, which we are going to call V. We multiply by current, which we are going to call I, and time, T. Therefore, work is given by V, I, T. Work is given by V, I, T. Work is given by V, I, T. Now, I will illustrate the same by way of example. And here, we consider solids first. Solids first. Solids. And for the solids, we only take care of the electrical energy being the same as the amount of energy that is transferred to the solid. So you are not going to look at the surrounding, you are not going to look at anything else but the only solid for which the temperature has risen. Now, let me take an example. Let me take an example. A metal cylinder Now the question reads, a metal cylinder of mass 0.5 kg is heated electrically using a voltage of 15, a current of 3 amperes, and that has been supplied within 10 minutes. Now we want the rise of temperature to be assumed to be from 20 to 85. Then we are supposed to write or to calculate the specific heat capacity of the block. Specific heat capacity of the block. Now, we have our V as 15 watts. I is 3.0, that is the current. Then the time is 10 minutes. Of course, we change to seconds by multiplying by 60. Then we have the mass of the block given as 0.5 kgs. Change in temperature is 65 degrees Celsius. Then we are supposed to calculate the specific heat capacity of the block. The specific heat capacity of our block. Now, with the kind of information that we have, let us equate work done by current or by electric energy. We equate it to heat gained by the block. That work done by the electrical energy is actually equal to the heat gained by our block. Now, in this case, work done is given by VIT, which is the same as the product of mass of the block, change in temperature of the block, and the specific heat capacity of the same. I will want us to substitute so that here we have 15, we have I as 3.0, our voltage is 15, we multiply by 3.0 and by 60, which is our time, is given or is equivalent to 0.5. We multiply by our temperature change, 65, and then by the specific heat capacity of the block, which we seek to determine. Let us resolve the sides and the left-hand side gives us 2,700, which is equivalent to 32.5 CB. We have not used a subscript. We have not yet determined the specific heat capacity, so we still have to divide both sides by 32.5 so that now our specific heat capacity becomes 83.1 joules per kilograms Kelvin. So you remember that the work that has been done by electrical energy is what we actually take to be equal to the block, the heat gained by the block. Now, the losses to the environment here are assumed to be negligible, and that way we can equate the two, and the figure we get is relative depending on how efficient our apparatus were. That's about all for today. Next time we meet, we are going to look at how we determine the specific heat capacity of liquids when we are using electrical method. Thank you.